We are a company and we have built a controller for line following of boats. And we want to sell this controller to a client which is far and which has a big boat, but the big boat is used for some other task and we are not able to use this boat for some tests. The controller has been designed for catamaran. So here we have a picture with a catamaran, and for the catamaran we are able to control. We have two propellers on the back, and for the sensors we have a compass, a Doppler log for the speed, and a GPS. So we have plenty of data from the client, and from this all this data we'll be able to have a good idea of the behavior of the boat. So we'll be able to build a model, and from this model we will be able to simulate and test our controller. The controller is given by this, so U1, U2 is given by this formula. And what we have to do first is to simulate this controller on a Dubins car model, just to understand how it works, and also to explain the principle of the controller. So the controller is given by this, and U corresponds to U1 and U2. So what we can do, we can take this matrix to put on the size, to inverse it, and we will get that U1 plus U2 and U1 minus U2 equal 2 divided by 3 multiplied by the vector tangent hyperbolic of 1 minus v, and here sine of something which is minus tangent hyperbolic of y divided by 10 minus theta. Okay. So what does this mean? This corresponds to some kind of error on the speed, and the tangent hyperbolic, let me recall that the tangent hyperbolic is something like this. Okay, with here minus 1 and 1. So what would happen if the speed of the boat v is less than 1, then u1 plus u2 will be positive. It means that the propellers will tell the boat to go forward. So it corresponds to some kind of acceleration. Now this one is a differential, so it means that if u1 is greater than u2, then the robot will turn. So how it works? This corresponds to some kind of error, and the line to follow here corresponds to y equal to 0. So if I am above the line, for instance here, then this quantity will be negative, and this angle will be something like this. If I am near to the line, I am like this. So if I'm here, I will go like this. If I am on the line, I will go right, if this is equal to 0. And if I am below the line, then the heading to follow will be like this. So what will happen is that my boat will try to follow some trajectory like this and will converge to the line to follow. As soon as this is equal to 0, it is the behavior that is expected. Now this can be viewed as an error, E, on the heading. It means that if the error is 0, I follow this vector field which converges to the line, but if not, I have some kind of proportional control that will make the robot turn so that I will follow the vector field. So for this situation, what will happen? First, this will not be equal to 0. My robot will turn like this, and then will converge, will follow the field, and will converge to 0. I will now consider a Python program for this. So I will use the RobLib library. This is a procedure to draw the boat. This is the controller. So here I enter the state x, y, theta, and v, and then the controller will return me u. For the simulation, I need some state equation for the Dubins car that are given here. Here it is my initial state, and I have a loop with an Euler integration chain that will simulate my Dubins car just to check the behavior of the controller. I switch to Python. I run the program, and I see that my Dubins car will converge to the line y equal to 0. Question number 2. The client has his own boat, but he has no model for it. It does not behave like a Dubins car since it slides sideways, which is not the case for a Dubins car, when it rotates. So since the boat has to do some other tasks, no possibility after discussion with the company to do any experiment. Of course, we have plenty of data, and how from this data I can extract a model, a state space model for it. I will first explain this. If I consider a state equation, so a dynamical system described by a state equation of the form x dot equal f of x, such as this one, then I can represent like this with an integrator and a function, which is an analytical function. So this is not a differential equation, but the loop corresponds to this state equation. So when I want to identify a system, I just need to identify the function f. So this function f goes from Rn to Rp, and I represent like this. So to x and u here, I have to associate x dot. So I will assume that I have many points for different t where I have x, u, and x dot. So it's a very big file, and each line corresponds to a given t. So I have each line corresponds to a position for my boat, but also I need to have x dot. So we'll see that this one can be obtained usually using accelerometers, and the other one can correspond to speeds or whatever. At this moment, I don't care. I just need to understand that I need both x, u, and x dot for different t. So I represent like this many data. So each point, green point here, correspond to one line. So 1 point, and so on. So I represent like this, and the function f should normally fit all these green points. But of course, f is not available, and I can only have an estimation for this. And this estimation can be represented by polynomials, for instance, with a Lagrange polynomial or Fourier series or whatever. But in our context, it will be convenient to use a neural network, such as this one, which is a multi-layer perceptron. So as soon as I have this, then from u and x, I will be able to predict what is x dot. So it means that if I have u and x here, I will predict here with the red the value for x dot. But of course, if the data are not everywhere, and if I try here, then I will have a big error between the behavior that I predict and the true behavior. So it is important to only use this function f hat, the estimation, only on when x and u are on the right place. Okay. So for dynamical system, most of the time I don't have to act like this because this function can be decomposed into two different blocks: the dynamic block and the kinematic block. So this one is the kinematic block, and the state vector for the kinematic block is q, corresponds to the degrees of freedom, and p corresponds here to the speed. So if you want, the derivative of the degrees of freedom. So in this model, phi contains many unknown parameters, such as the mass, the inertial matrices, the friction coefficient, or whatever. But this one is almost exact. So I don't need to learn this one, since I know it, and it is the same for all boats, as we will see in the example later. So for the estimation of my neural network, I will use activation function. So activation function sigma of x, which will be given by ReLU of x, which corresponds to the maximum of 0 and x. So ReLU means rectifying a linear unit. Okay. And this function is something like this. When x is here, it will be 0 when x is negative, and after it will be like this. And from this function, I will be able to represent almost all functions from f from Rn, R to R. So I will try to explain this now. For instance, the triangle function can be represented by this sum. So let me explain why. So here it is my activation function, my ReLU function, sigma of x, and we can easily understand that this one corresponds to this triangle function. And by the sum of triangle function, I can represent any function from R to R. For instance, if I want to represent the sine function, for instance, f of x equal sine of x, so here it's of t, then I can see that if I sum all the green triangle, I will obtain the red function. But if I have different sampling time, the sum of the green function will almost represent the sine function. But if I am not on the right domain, then the interpolation will be 0. So the interpolation is not good anymore. So it's not exactly an interpolation, but not what we call an extrapolation. So the approach will not be adapted to extrapolation. For function f that goes from Rn to Rp, for instance, for R3 to R2, then I will need to have more composition of ReLU function and not only sums. So if I have only sum, it means that I have only one layer, but here I can observe that I have different layers. This one is what we call a hidden layer. This one also. This one is the input layer and this one the output layer. Each arc corresponds to a Relu function of the form A sigma of x plus b. B is what we call the bias, and here the scale function. Each arc corresponds to, of course, a different one. And what I will have to do is to tune all parameters A and B for all arcs so that this function corresponding to f hat will be similar to f. Okay. So for this, to tune A and B, I will use a non-convex minimization method. As said previously, the client provides a file where I have many recorded data. And from this data, the behavior of the boat can be extracted. So the file is given for this exercise and is named deepboatdata.txt. And we have thousands of lines. If each line corresponds to a line vector for a different t, given here. And from this file, I am able to have an approximation of the function phi, which provides me the function phi from Vx, Vy, from the speed, from omega, and from the input, from the actuators, will give me the acceleration in the direction of x and y in the robot frame, and also the derivative of the rotation rate. Okay, so it means that the actual robot of the client has not a speed in the like this. The speed is more like this. Up. The speed is more like this. Okay. So here it will correspond to Vx now, and this one will correspond to Vy. Okay. So due to the fact that I have some sliding effect. It's not a Dubins car. So phi give me this, and the data file is like this. Many columns for different t, and the first column corresponds to Vx, Vy, omega, U1, U2, and after I will have V dot x, V dot y, omega dot. Okay. So here the first line, the second line. So this one is, for instance, for t equal to 0, for t equal O dot 1, and so on. This file is huge. And what I will now do is from this, the function phi will give me this. So how I generated this file, I will explain you in Python. It's not asked in the exercise since the file is given, but I will just explain how I have obtained it. Okay, so I have a loop. I take randomly some initial condition, and I made a simulation up to t equal to 10. And I draw here the robot sometimes, every second. Okay. Then I extract the vector and I save it in the file deepboat data. I run it, and I have here a lot of simulation. Now I have my file deepboatdata.txt, and it contains all information that will allow me to estimate phi. So I have to compute this approximation. For this, I will use TensorFlow here, and I will build my function phi hat, which will be an approximation of phi. So recall that phi has 5 input and 3 output. So this is why when I build my model, so the Keras model, I will take 5 input and 3 output. So it means that here I will have 3 input, like here, 5 input, but here instead of 3. But here I will have 3 output instead of 2 like here. Okay. I will use for the hidden layer also 2 hidden layer with 32 and not 4 and 32 here and here. Of course I can put more, I will be more, the approximation will be better, but the computing time will be larger also, so I have to take care of this. So 2 hidden layer is quite classical. Then I tune my optimizer, and the optimization will be done with a criterion which is a mean square error. I will load my data, and then I will fit, so I will tune all my parameters. So the here is the number of iteration. Here the 5 first column of my file deepboat, and here the 3 last column. Okay. Then I will be able, once M has been built, I will be able to predict it with Vx, Vy, and so on. U1, U2, I will be able to predict and to transform into a vector or a list. It will predict, so give me this one, so this one, and this one. Okay. Now I have built this function phi. I have built phi-hat, and I will return it. So my function build-hat will return me a function. Okay. So this is why here I have phi-hat is equal to build phi-hat, and now phi-hat will be a function. I will be able to call it for my simulation. Question number 3. Deduce a learned state space model for the client's boat. And the state vector is taken as here it will be Q, the degrees of freedom, and here it will be P, some kind of derivative of the degree of freedom. So recall that the state space model is here, is equivalent to 2 parts, so the kinematic part here and the dynamic part here, where P is involved, and this one is known exactly. So it corresponds to psi, is known exactly, and it's just some geometry, and no coefficients are here. So Q, so let me explain here. It's just I will explain that my boat is here with theta is the heading. Here I will have Vx, here I will have Vy, and we understand that we switch from Vx, Vy to the word frame by a rotation matrix, and this rotation matrix R will corresponds to cos theta minus sin theta, cos theta, it's a rotation matrix, and if I multiply by the vector Vx, Vy, I will reach x and y, so the derivative of the position x and y in the word frame. So this is just geometry. And this one also no coefficient, just tell me that the derivative of the heading corresponds to the rotation rate. The input of this system is P, so P is here, and we understand that the derivative of P is equal to the function phi, where here I have P, and here the input U. And I have learned this one. This is why here I have phi-hat. Question number 4. Illustrate the behavior of the learned boat for the line following task with our controller, of course. And the initial state vector is given by this. So let me recall that the state vector x here x0 means x corresponds to x, y, theta, and also vx, vy, and omega. Okay, and recall that it is given here. So I am able to obtain the derivative of x, y, theta, and of vx, vy, and omega thanks to all these formulas. So for the simulation, I will have to express the derivative of x dot as a function of x and u, and it is this function I call f dynamic, which enclose all. So here this corresponds to this, and this corresponds to the function phi that is given as an input of f dynamic. So of course for phi I will put phi hat that has been built previously. So for the simulation, I will have a for loop. I will draw the boat and use the controller. But the controller I've made for the Dubins car, which only asks for input x, y, theta, and vx, no vy, of course. But I will use here f dynamic with an input phi hat that has been built previously, and that is used here, of course. And this will perform a simulation of the boat of the client that has been learned from all the data here. This is my function. I run it. And I can see that the car slides on the right due to the fact that it turns, like a car moving on the ice. And then after, it may converge to the line. So I can see some overshoot. I may not be satisfactory, but I can observe the behavior that I can expect on the real client boat. The day of the first experiment, where we'll test our controller, we'll have the actual boat, of course. But for this exercise, I will assume that I have the client boat and that the data have been generated by this model. Okay, so I want to test the microcontroller and with this model, and to compare with the model the behavior that has been predicted by my neural network, by this one. So this corresponds to the actual phi, and phi hat here corresponds to the one that has been trained. Okay. So the Python program I propose is I replace phi real, so phi, the phi, by this one, and we see that in this model that for instance the controller, the actuator 1, the propeller 1, is more efficient than the second one. I can see here how the friction has been generated. I can see also here some coefficients that are not easy to tune in general. I can see also this coefficient, which tells me that my robot is sliding when it is rotating with a speed which is proportional to Vx. So I'm not sure that this model is good, but it is the one I have used for training my neural network. So here it is a copy of that. I take the same initial condition. I have my loop, and here I use the controller of my Dubins car, and I will simulate using f dynamic, but this function here is the real one, not the one from the perceptron. this is a simulation with my train boat using the neural network. And after I will compare with the real boat here. So I can see some similar behavior, but it is not exactly the same trajectory. But the behavior is the same.